this is the final lecture of this course. But maybe just this course is just the beginning for you for more courses in dynamics that you will take in your future careers. And so I want to take this as an opportunity to kind of review a little bit what we did and also mention further directions for the field, yes, to give you some idea. So, of course, I've said many times that the fundamental core concept, at least of the second part of the course, is that of a physical measure. Which is if you have a measure whose basin has positive Lebesgue measure, so we assume we're on a space. By Lebesgue, in more general spaces, there's some reference measure that is in Riemannian geometry is the volume of your manifold. We sometimes even call it Lebesgue measure. And B mu, of course, is the basin, as you know. So there are three fundamental kind of channels, directions in this area. The first one is to identify possible physical measures. And the second one, I would say that it is about verifying the existence of these measures in specific systems. Verifying existence in specific systems. And the third, which I've not talked about at all, but I will talk a little bit about it now, is about going deeper into the ergodic properties of the measure. So for the moment, the only tool, the only motivation for the invariant measures we have is Birkhoff's ergodic theorem, okay? That tells us something about the time average as the distribution. But it turns out that many measures have you can study much more in detail ergodic properties, and I will explain a little bit what I mean here. So let me say further ergodic statistical properties. So a lot of work in dynamical systems is related to these three sections. I just want to emphasize that there's also a lot of work, as I said before, in studying other measures that are not physical but have dynamical significance. Okay, so there are many other measures. We saw in the map 10x mod 1 or 2x mod 1, there's an uncountable family of measures. There's the Dirac measures, there's these measures that are, that live on these sets which have different asymptotic behavior, so they can have different editors. It's just the focus of this particular course, and it's also the focus of a certain area of differentiable dynamical systems that it is. So let me say first of all a little bit about one. So which measures do we know that are physical measures? We've looked at two kinds. Yeah, what's the easiest kind? Remember? What's the easiest physical measure you can have? The simplest? Yes, when you have a fixed point. If you have an attracting fixed point, right? If you have an attracting fixed point, the Dirac delta on the fixed point is a physical measure. Okay. More generally, I've not really given some examples because it's not that easy to see them, obviously. But you can also have an attracting periodic orbit. So you can have a periodic orbit. You can put the Dirac delta there. The fact that it's attracting means that each neighborhood, each point along the orbit has a neighborhood, and the points, they move around with the periodic orbit and they converge to the periodic orbit. Okay, so the simplest is the Dirac delta on attracting periodic orbit. So you can have, for example, orbit of period 3, P1, P2, P3. One easy way to look at it is that periodic orbit is a fixed point for F3, right? So it just means that you have neighborhoods of these 3 points, and the points in this neighborhood, they map to this, they map to this, they map to this, and in the meanwhile, the point is getting closer and closer to these 3 points, and therefore it's converging to the Dirac delta on these 3 points. Okay? And the second one, what we've been working on a lot, are measures that are ergodic, invariant, and absolutely continuous with respect to Lebesgue, right? So, mu, ergodic, invariant, and absolutely continuous with respect to Lebesgue. So we saw this has been in some sense, the main topic that we've discussed. These are physical measures because of Birkhoff's ergodic theorem, right? So Birkhoff's ergodic theorem and the absolute continuity guarantee that the Lebesgue, this is automatically, if you have a measure that's ergodic, invariant, and absolutely continuous, then it's automatically. So I will discuss a little bit now the existence of these 2 measures in one dimension. So that in one dimension these, well, let me say first that in higher dimensions, there's a third class of measures, okay? In higher dimensions, you may get something that is a kind of combination of these 2. So in higher dimensions, you may get a situation where you have an attractor, but this attractor is not periodic. So you have some non-trivial set here, lambda, okay, where f of lambda equals lambda. So this is an invariant set, just like a periodic orbit is, but it's not a periodic orbit. It may have a kind of chaotic dynamics like the 10x mod 1, like these systems that we've looked at, but it is in higher dimension for diffeomorphism, right? And in this case, you may have an attractor, so you may have points converging to this, but the general setting is that in general, Lebesgue of lambda is equal to 0. And any measure, therefore, supported on lambda, any invariant measure has to be supported living on the attractor, right? Because, as you know, you don't have recurrence. Always, if this is an attractor in the sense that points are converging to lambda, then any invariant measures cannot give positive measure to these points, because these points, they move towards lambda and they never come back, because lambda is an attractor, right? So any measure needs to be living on lambda, and if lambda has 0 measure, a measure that is, you know, where the only points that are positive measure are points on lambda cannot be absolutely continuous, right? So any invariant measure cannot be absolutely continuous with respect to Lebesgue, okay? So we have a bit of a problem because we do not fall into either of these cases, okay? And this is exactly, so there is a class of measures called SRB measures, okay? So senile Wellborn, SRB measures, okay, on, I will write this hyperbolic attractors, although I have not defined this properly yet. But in higher dimension, this is a natural generalization, if you want, or an addition that combines a little bit these 2 properties. This is a very common feature. And hyperbolicity is a generalization of the expansivity that we've been talking about. So a crucial property of the maps, one-dimension maps we discussed, is that the derivative is bigger than 1 everywhere, right? We show that when the derivative is equal to 1 at a fixed point or at a 0 point, then there's some difficulties. In higher dimensions, you have you have a derivative is a map on the tangent space, and you can have the tangent space splitting into some directions that are contracting and some are expanding, and that is behind the definition of hyperbolicity. So you can generalize this notion that you don't have points where the derivative is 0 or 1. I will not go into it, but just so that you know, this would be really a second course. So if I was to give a second course, I would move on exactly to this, to give the definition of hyperbolicity in SRB measures, right? Hyperbolic dynamics. Here I just want to tell you that they exist, and this is the natural generalization. So there is a kind of conjecture that most dynamical systems, if they have a physical measure, is of this type. But there are many other physical measures. There are some very strange physical measures that you don't expect. Okay, so in fact I will show you one that's not so strange in a minute, but when I talk about this. But anyway, this is a kind of basic picture of the possible physical measures or natural physical measures, and there's been a lot of study in the last few decades trying to show many systems that have this kind of physical measure, which brings us to the second part, of course, which is what it's really about. There's not much point identifying a physical measure if the kind of physical measure, if it's very pathological, if it's exceptional, if you cannot verify it in any examples. So we have already done a lot of work showing that you have this kind of measure in full branch, uniformly expanding maps, and also using the inducing, right? You can extend that to other maps differently, okay? So I want to give you here just a little overview of some very interesting family that has been a kind of test for the field to really test the limits of the techniques of what we can do, even though it's a very simple map. Let's put it as with a parameter, family of maps, x squared minus a. So one of these maps we've already studied, right, which is the case a equals 2. Let me put it here. So here we've got a equals 2. We have, so this is really a map from R to R. If you think of this as a map from R to R, what happens to the points outside? I've always concentrated on this interval minus 2, 2. What happens to the points outside this interval? They go to infinity. Is that clear? Yes? So it's easy to see. So here the map goes up here. This is the diagonal. So if you take a point here, it will just go to infinity. If you take a point here, it will also map to here, and then will go to infinity. Okay? So the reason I've concentrated on minus 2, 2 is because nothing interesting happens otherwise. Okay? What happens for a greater than 2? So what happens here? Because the box is also a little bit misleading. Let's draw it first as just as a map like this. Okay. There's a fixed point here, there's a fixed point here. So what happens for a greater than 2? So what in the picture, how can you identify the parameter a from the picture?
Okay, a is just the intersection with the y-axis.
Exactly. It's the image of 0, right? If you put x equals 0, you get minus a. Okay? That's why we have minus 2 here. Okay? So if we have, so here we have minus a. Sorry, a. Yes, here we have a. Here we have minus a. So what happens when a is bigger than 2? this is less than -2, so this is going down. So all this is a translation of this parabola, right? This is just a parabola x squared, and you just push it up and down. So we're going to look at what happens as you push it up and down at the moment. We're going to do like a brief analysis and see what happens for different parameters. Now, it just so happens that you still have these two fixed points. So you have, you have this fixed point, and then you have the pre-image of this fixed point, because that's what these two, this is how these two boundaries, this is how this interval is defined, right? Notice that this is defined by the fixed point here. At the point 2, the reason why I put this box, although I didn't say it before, is because you have a fixed point here exactly at 2, okay? And the pre-image of this fixed point is -2. Now, as you push this down, what happens to this fixed point? Is it moving to the left or to the right? Or is it staying the same?
It's moving to the right.
It's moving out, right? So this point is moving to the right and this point is moving to the left because it's the pre-image. So the fact that this is moving to the right corresponds to the fact that it's moving up here. Yes? So the box, if I want to draw a box here with these on this fixed point, it is getting bigger, right? And is this going to be inside or outside the box? Because this is moving down, but the box is getting bigger. So do we continue? Do we still have the box exactly like this? Does this picture continue to hold or not? It's not actually something that is obvious to see. You need to do a little calculation, but it's not a difficult calculation because you can actually calculate exactly this point, right? You can just like x squared minus a equals x, so you can calculate the formula for the fixed points, okay? And I'm not going to do it, but if you do it, you will see that this point moves slower than this point, okay? So in fact, this point has moved slower, so you can find this code, this point here. You can find this fixed point explicitly, and you will see that you will get something like this. The box is getting bigger, but more slowly than this is moving. So as soon as you go to a greater than 2, even for a equals 2 plus epsilon, this tip is moving at a positive speed faster than this is moving to the right, so it comes out of the box. Let me leave this as an exercise here. I think this is an interesting exercise. Show that how shall we say that the fixed point, that the positive fixed point. So we always have two fixed points. One is a positive, one is negative. So the positive fixed point, P of A, is less than A. Less than A. Right, that's what we're saying. Because this point here is A. Okay, and this point here is P of A. Here, P of A equals P of 2 equals 2, and here P of A is less than A. And what happens, do you think? What's the dynamics in this picture here? So outside this interval here, what happens? Outside this interval, minus P of A, what happens? The same thing as before. Yeah? So outside this interval, the same thing. So everything goes. So all we need to worry about is what happens inside the interval. And what happens inside the interval.
And there are some intervals also, the pre-images of this interval,
which escape. Okay? This is very similar to the picture that we did. Remember in the first part of the course, we looked at the fact that here we have points, we have an interval here that escapes. Right? Because all these points escape here, and they move outside this box, which means that when you iterate once, that the next time they arrive here, then the next time they arrive here, and then they go to minus infinity. Okay? And then you have the preimage of this and the preimage of this, and the question is, does everything escape? And it turns out, so the only difference between this case and the case we did is that here we still may have very small derivative, right? Because if A is just 2 plus epsilon, then you just have the tip, so you do not have the expansion, right? Remember, we did with the tent map, we did all the calculation, and we showed that there's a Cantor set of points that survives inside, right? We did it all, and it turns out that here it's exactly the same thing. Okay, so there is an additional technical complication. We'll not do the calculation, but there's an additional technical calculation because we use the fact that the map, the derivative is bigger than 1 everywhere, okay? So here the derivative is bigger than 1, but here it's less than 1, and sometimes you may have just a very small tip, but nevertheless, even if the tip is tiny, you can show that almost every point eventually escape. And what you're left with is just a Cantor set of measure 0. Okay? So this case is in some sense not, well, it's interesting, but it's done. Okay? And this happens for all A bigger than 2. This picture just gets bigger and bigger, but it's exactly the same picture. Okay? So the more you iterate A, the tip comes down, the box gets bigger, but the box never gets bigger fast enough to re-include the tip. Okay, this box gets bigger more slowly than the tip comes down, so you always have exactly this picture. Okay, so that's for all A less than 2. What about now for A bigger than 2? Like for A equals 0, for example. So now let me draw, I'm going backwards here, but okay, so for A equals 0, we get just a standard parabola, right? We still have 2 fixed points. Where are the fixed points now? The diagonal, we have a fixed point at 0, which corresponds to this one, and this fixed point is where? What's this fixed point? How's that? Yes. 1. Yeah? This is 1. Are there any parameters for which there are no fixed points?
Yes.
Yes. If we draw the parabola here, okay. So for all A, let's say, sufficiently negative, this is when A is equal to 0. When A is positive, we're moving down, right? When A is negative, we're moving up, okay? So for A, not even much less to 0, you can calculate. There is one parameter in which this map is tangent to the diagonal here. And that's the first time that a critical point, that a fixed point appears, right? So for all the parameters less than this, so you can calculate. You give another exercise. This is a simple exercise, but calculate parameter A such that f of A has a unique fixed point. Okay, you can just put, so the equation for the fixed point is just that fa of x equals x squared minus a equals x.
With discriminants here.
Yes, exactly. Okay, it's just a quadratic, and in fact, what you have is you divide the parameter space into 2 regions. Below this region, for A less than this region, you never have 0 fixed point, which corresponds to having 0 solutions to this equation, 1 solution, and then 2 solutions everywhere else. Okay. So you can easily calculate this. So what happens, what's the dynamics in this case? Let's call this a 0, this particular parameter that corresponds to this. What happens for A less than A0? In other words, where there's no fixed point, what's the dynamics? You take a point x here, you map it to here, map it to the diagonal, map it to here. What does it do? They just go to plus infinity, everything, okay? Here you take a point here, maps to this. Everything is above the diagonal, so everything is always increasing, right? Remember, if you're above the diagonal, it means that your image is to the right of where you started. So you go here, and then you go above, and then you keep going faster and faster, okay? So for all a less than a0, so let me write this. Let me start to write some points. A0 equals A0 is the such that f of a has a unique fixed point. Okay, so for a less than a0 implies that fnx goes to infinity for all x, right? Everything just goes to infinity for those parameters here. What happens at this parameter? At a equals 0, a equals a0. What's the dynamics in this parameter?
That's a fixed point, so I think and draw a region when everything converges to these fixed points, and outside this region everything.
Exactly. It's a very remarkable thing here. This is an example, in some sense, of a bifurcation parameter, right, which we've not discussed before. So all of a sudden, for any a less than a0, everything goes to infinity. Okay? And then all of a sudden, you've got a fixed point now. And what happens to this fixed point? Well, you can see that if you take a point close to this fixed point to the left, then it's going to converge to the fixed point. Right? Because locally, it's just like the pictures we saw before. You have a fixed point. How far is this going to happen? It's going to still happen to this. It's going to still happen to this. But of course, if you start here, then it's going to skip the fixed point and it's going to go to minus infinity, to plus infinity. So you take the pre-image of this fixed point. This is the fixed point P of A. This is a fixed point P of A. This is minus P of A, right? And now suddenly we have an interval of parameter values. Sorry, an interval of phase space here, where all the points in this interval, they converge to this fixed point. Yeah? Is that okay? You see this?
Yeah.
Yes? How can you explain that, actually, that, you know, there's like some kind of discontinuity in the map, because these points here, for this parameter, they converge to the fixed point. If you take a parameter even infinitesimally smaller than a0, then they go to minus infinity. How can you explain how you can have this kind of, I mean, suppose you don't know exactly what parameter you've got. I mean, what is this point doing? If you take a point here, right, and you iterate it 1,000,000 times, it's going to be very close to PA because it is extremely close to PA. Okay? What if you take a parameter very close and you iterate it also 1,000,000 times? It should be still close to PA. But now we're saying that it's going to infinity. How can you reconcile these two?
Maybe because of the derivative, for instance, of the fixed point is 1 to 1. And maybe before the fixed point is less than 1. I don't know. Yes, less than 1, and after it's bigger than 1.
Well, so what happens is that it just takes a very long time to get past. So both of these things are true, of course. So if A is less than A0, then this point here, which was converging to P of A, it eventually goes to infinity. But it takes a very long time. So if for this parameter value A0, after 1,000,000 iterates is very close to here, if you take a parameter that's very close, what will it look like? Let's just zoom in to here. So let me draw a bigger version of that, right? So this is the diagonal, right? And suppose our map is very close. The parameter is very close. Okay, so there's no fixed point, but it's very close. So what happens when you iterate a point, you've got a point here, and you iterate it, and it goes like this. But as you can see, it is taking a long time to get past. Okay? If there's a fixed point, it does not get past at all. If there is not a fixed point, then eventually it will get past and then, but it will spend a very long time in that. So there is a continuity of this in the sense that if you look at a point and you iterate it 1,000,000 times, it comes very close. Then obviously if you take a parameter small enough, then this point after 1,000,000 times will still be in this neighborhood. But after 1,000,000,000 iterates, it might have escaped and might go to infinity. Okay, this is another very nice example to distinguish again in a very subtle way between the topological behavior and the time averages behavior, right? When you just talk about the omega limit of a point or the asymptotic limit, in this case, this point goes to infinity. And strictly speaking, even when you look at the limit of the Dirac measures, they just go to infinity, right? But sometimes there's some subtle dynamical phenomena that occur in finite time that are relevant, or may be relevant in your situation, right? So this is an example in which it's a situation where you just look at it and you say, okay, all the points, they just go to infinity, but in this case, even though it goes to infinity, it spends a huge amount of time in the neighborhood of this point. So I'm just trying to point out some subtleties that there are, that you keep encountering, okay, when you try to describe the dynamics of a certain situation. Okay, any questions? Okay, so this is what happens up to this parameter A0. So now what happens as we push it below A0? What's the picture now below? So below we now have, if you just put a little bit below, then we have this. Okay, because you push this a little bit below and now you have two fixed points. So what's the dynamics now? So here we still have this P of A, and we still have that to the right of P of A you still go to infinity. Right? And we also have the pre-image of P of A. And we have to the left of P of A, you also go to infinity. Okay? And we have now still an invariant interval here. Except that this invariant interval, now the situation is a little bit more sophisticated. Because we have another fixed point in the interior.
Every point goes to another fixed point.
To which one? To this one or to this one? To this one.
Yeah.
Because what's the derivative of these two fixed points?
Derivative on PA is bigger than 1. But in this point, as a fixed point, is smaller.
And how do you know that?
Just tangent is
Exactly, because here it was 1. Right? Here the derivative was 1. Because this was the point. So when it was tangent to the diagonal, it necessarily has to be tangent where the slope is 1, because the slope of the diagonal is 1. So when it's tangent, so when you calculate in the exercise, you calculate the parameter for which you get a unique fixed point, you can also calculate the position of this unique fixed point, and you can calculate the derivative of that fixed point, and you will get the derivative is equal to 1 in that case. You can calculate that. And so obviously when you push it, you see, you push it, so this point here, you're just pushing the whole thing down. So this point, when the derivative is 1, will come below the diagonal, and you will be left with two intersections with the diagonal, which therefore clearly one of the derivatives will be less than 1, and one of the derivatives will be bigger than 1. Okay? And which means, as you know, if the derivative is less than 1, the points are attracting. Okay, I'm not going to give a formal proof here, but you can very easily formalize it. So you can see that if you take a point here, it is going to converge to this fixed point From this side, if you take another point here, everywhere on this side, it will converge to here, and therefore all of them will, right? Because if you take any other point, either if you take a point here very close to this, it will converge directly. Okay, this one has a kind of pre-image also. So in this smaller interval, they will converge on this side. If you're outside this smaller interval, then you will map into here, and then you will converge from the other side. Okay? So here you have an interesting situation where, so now you have an invariant interval, and we have a single periodic attractor that attracts everything. Yeah. Okay? So for a greater than but close to A0, we have a unique attracting periodic orbit. So let me write it like this to say that it's close to A0 implies there exists unique attracting fixed point. In this interval minus P of A, P of A. I'm going to use P of A. So here I'm going to start using P of A to mean there's always going to be one fixed point more to the right and one fixed point more to the left, right? So this fixed point is going to continue for all parameters, obviously, because now as we move the quadratic, the parabola down, there's always going to be some point of intersection here. We're just going to, it's going to be moving out all the time. What happens as we move further now? Okay, we're trying to do systematic analysis here. So here we have this fixed point. Let's look at the parameter value A equals 0. What do we have in the parameter value A equals 0? We have exactly the same picture, right? It's just here, this other fixed point has derivative 0, but essentially you have still the same picture where you have this parameter P of A minus A. Sorry, in this case this is 1, this is minus 1. Okay, everything outside goes to infinity, and everything inside does what? Converges to this fixed point. Right? So you take a point here, and it just converges to this fixed point. You take a point here, and it maps to here. Right? It maps to here, and then it converges to the fixed point. So there's essentially no difference from here to here. What you're doing is, as you move it down, this point is moving to the right, this point is moving to the left, of course, until here. And what happens when we get past this? So when we get past this, something starts to get interesting. So when we get past this, when we get a little bit past this, there's still nothing. So this is P of A. This is minus P of A. This is the fixed point. What's the difference now between this situation and that situation? Is this still an attracting fixed point?
No.
No? Why not?
Both of them are.
Maybe observatory of derivative is
Well, this cannot be attracting because the derivative is bigger than 1. Okay? What is the absolute value? So now this derivative is negative. But what's the absolute value of the derivative here? It's very close to 0. If we just take a little bit closer, then the derivative here is 0. So, you know, if you've just gone down a little bit, the derivative here will be close to 0. It will be negative, but close to 0. Okay? But the derivative is negative, so the picture is a bit different. But you know that if the derivative is close to 0 and negative, the second iterate, this is a fixed point, so the second iterate is still a fixed point. And what's the derivative of the second iterate?
It's all positive.
Positive and still close to 0. which means less than 1, which means it's an attracting fixed point for the second iterate of the map. Okay, which means it has to be an attracting fixed point also for the first iterate of the map. But what does an attracting fixed point with a negative? So if you have, if the graph looks like this, so this actually we did not, I don't think I talked about. We could have talked about it when I looked, in the topological part, when we looked at the attracting fixed point. I didn't spend much time, but it's curious when you have a negative. Let me draw it even closer to 0. Okay, so this is negative, and it's a very small derivative, a little bit like this. Okay, so what do the points do? So here you have a point x here. Okay, you iterate it. And now, because this is below the diagonal, on the one hand it's easier to do it when it's small, on the other hand it's easier. Let me just do it a little bit bigger, okay? So I map this, and if you remember the way I draw the diagram, now I have to go to the diagonal here, the way I draw these web diagrams, right? Because this point here, I reflected on the diagonal to get its image, which means because this is negative, then this point is flipping to the other side of the fixed point. This is some point Q, right? Because this is negative, the derivative, then it means that the slope is going down, the graph is moving down, which means that the image of this point on the right is actually less than this point here, which means that it's on the left, on the thing, okay? So this goes here, and then the same thing. So now we want to iterate this one, but for the same reason, this moves to the right, and actually you get a kind of spiral again like this. Okay, so when the derivative is negative, what this point is doing is still converging to Q, but it is flipping sides each time. I think we did one example like that at the beginning, where you have negative, like in the linear case, when you have negative and you're flipping back and forth. Okay, so that's exactly this situation here. Okay, it's flipping back and forth. So here you still have a unit attracting fixed point. It just happens to be orientation reversing, so the way the orbits converge, this is a little bit different once you do that. Okay, but now we go further, so we keep. At some point, what's happening now as we push this further and further down? So this point here, nothing much happens, right? The derivative is always going to be bigger than 1, and it's going to continue to be bigger than 1. This is moving. But this point, at some point, you see it's moving down, right? So at some point, you will get this. And at some point, wait, let me not draw it like this. At some point, you will reach a moment where the derivative is no longer less than 1, where the absolute value is no longer less than 1, because at some point, you will have a moment where here, the derivative, this is a point Q, where the derivative at Q is equal to -1, right? And then if you go a bit further, the derivative at Q will be even less than -1, right? So the absolute value So what happens now? We now have 2 points, so this is no longer attracting.
It happens the same because the second iterate has derivative bigger than 1.
It has derivative, positive derivative, but bigger than 1, right? What is the picture here? If you take a point nearby, it will still flip, but it's moving away, it's not moving towards. It's moving away. It's now a repelling fixed point. And this is also a repelling fixed point. Okay, so we now have still these 2 we still have this interval. This is P of A. This is minus P of A. We have two fixed points. We still have the two fixed points. But both of them are repelling. Okay, and again, there's a very strange situation about the fact that here, just before, there is this some parameter. Let's call this A1. So A1 is equal to the parameter where f prime of q is equal to -1. This is a kind of a special parameter. So the first moment in which things change, in some sense, are when A equals A0, when you have a unique fixed point, okay? Then after that, you always have these two fixed points where one of them is attracting and one of them is repelling, and we always have the same picture until we get to this moment, okay? This moment is a little bit trickier because one of the derivatives is -1, and after that, you get this -1. So what happens to all the point if you take a parameter that is a little bit before this moment, then this is an attracting fixed point and everything converges to this. And then suddenly you change the parameter by epsilon and this becomes a repelling fixed point. So what happens to all the points that were converging, again, the continuity, they were converging to this fixed point and suddenly this fixed point is pushing them back? Where do they go? They go what? To the other point? What's the omega limit of all these points? It can no longer be either of the two fixed points.
Infinity.
That's infinity.
Huh?
Is every point omega limit is just infinity.
No, because nothing can escape this interval here.
Ah.
Nothing can escape this interval here. So all these points, as you can see, outside this interval is like this, but this you can easily do a calculation. So I did not have time in the course. I don't want to focus on this. So I'm giving you an overview, and we're not going into full details about the examination of this. But the nice thing with this is that all these parameters you can calculate very easily, explicitly, right? With the formula, you can calculate the formula for these two fixed points, right? You can calculate the derivative of those two fixed points, so you can calculate exactly this parameter A1, you can calculate exactly which one it is. Okay, so it's very concrete, at least up to here, what we are doing. And you can see that for that fixed point, there is this interval is invariant. So this tip stays inside this box, right? So everything maps inside here. You can show it explicitly very easily.
So the omega limits are the extremes of the interval?
I don't know.
It's not possible to know.
All these points that were converging to this fixed point, and suddenly it's like, oh, let's move out. So something very interesting happens, which unfortunately I not have time, which is that even though I drew this picture like this here, if you suppose that you're very close to -1, so suppose you are less but very close to -1, okay, so you're just after this bifurcation here, what happens is that if you take a point very close to here, indeed it moves out, okay, but there happens to be one point here that is exactly periodic. So this is the point Q. So this is a point Q, and there are 2 points here that map to each other. Okay, and the picture is like this. The picture of that point. We cannot see this, but if you do the second iterate of the map, you would see that the second iterate now has 4 fixed points. So up until now, there were just these 2 fixed points, and there's no other periodic points clearly, because everything, as we said, is converging to this point or this point. Okay? But here we don't know where points are converging to, and in fact what happens is that we have just created a new periodic orbit. This is called a period doubling bifurcation. You create a periodic orbit. So this is a part of dynamics called bifurcation theory, which is very interesting, which I'm not focused on, but that shows how bifurcations happen, so how the dynamics changes for certain parameters, and this is one of the simplest examples, okay? And as the parameter transitions with a fixed point, goes through the derivative -1, immediately after that, often you get a periodic point of period 2, and this periodic point is an attracting periodic point of period 2. And that's where all the points are going to. Okay? So the points that were very close to this fixed point, they converge to this periodic point from inside. So if you take a point in here, it is flipping back and forth and converging to this. And if you take a point in here, it will also converge. If you take a point here, then it will go like this, and then it will go either inside, or if it goes here, then it will go here, then here, and then here, and okay, here. Anyway, eventually it will converge. So everything, all the points will converge to this attracting periodic orbit of period. Okay? So for A bigger than but close to A1, there exists attracting periodic orbit of period 2. And then again, I don't want to spend the whole lecture on this, but the interesting thing is then there is another sequence. If you draw the map of the second iter of the map, if you draw the graph of the second iter of the map, you can see that this periodic orbit of period 2 is a fixed point for the second iter, of course, and this fixed point, as you change the parameter, it undergoes exactly the same kind of bifurcation. It starts by having positive, of course, at this moment, the second iterate gives a positive derivative here, but then the second iterate, this point, as you change it, it goes to becoming 0, and it goes to becoming negative, and it goes to becoming -1, and then it itself undergoes another period doubling bifurcation, and it gives rise to a periodic point of period 4. So that periodic point becomes repelling, and it gives rise to an attracting periodic orbit. Okay, so we have a sequence A2, A3 of sequence of what's called period doubling bifurcations. Which accumulate, so the attracting, you get after at some point, at some parameter A2, this periodic, attracting periodic orbit of period 2 bifurcates and gives rise to an attracting periodic orbit of period 4. Then this periodic orbit of period 4, at some parameter A3, gives rise to an attracting periodic orbit of period 8. Okay, and that is always the unique attracting periodic orbit in this picture. Okay, and these AN converge to some parameter A star, which is approximately 1.4. Because remember, we had a different phenomena. We had this absolutely continuous invariant attracting periodic orbit, right? And this is sometimes called the Feigenbaum map. And Feigenbaum is, I think, a mathematical physicist, and he got very interested, even though this looks like a very simple phenomena, curiously enough, he got interested in the kind of rates how fast he saw that this converged, and he discovered a kind of universality phenomena that became very big in physics, because he showed that the speed with which this convergence happens, the ratio kind of between these successive, was a number called the Feigenbaum constant, which appeared in many other situations. Okay, so he discovered that incredibly there is some kind of universality in the speed with which these period doubling bifurcations occur. Anyway, I'll just leave it at that. So for this Feigenbaum map, you have a physical measure that is none of the other. This is one example where you have a different kind of physical measure, which I will not discuss so much. But then what is left is this. So up until here, the only dynamics that you have is an attracting periodic orbit and a few repelling periodic orbit. Because notice that every time you have this bifurcation, you create a new attracting periodic orbit, but you leave behind a new repelling periodic orbit, right? Because here, when you go here from this point, you started with just 2 fixed points, okay? And then what you left is one attracting periodic orbit, but this fixed point that was attracting has become repelling. So in this situation, you have 2 repelling fixed points and attracting periodic orbit. When that bifurcates, then this periodic point remains as in some sense, as a repelling periodic point, and it gives rise to period 4 attracting periodic point. So but you always have a finite number of periodic orbits up until this place here. Any questions so far? Okay. Okay, so I won't go now. I just want to give you some little overview of results, because in some sense the point of all this was to say that what's left is this parameter interval between 1.4 and 2. So after 2 we saw that nothing happens. So omega equals 1.4 to 2, okay, is the interesting parameters. Everything else is also very interesting, but somehow is also fairly elementary what happens here. Okay, and so we'll just really cite a bunch of research results about what happens here, which are very interesting. And it turns out that, so let's define, it's a subset of this, so let's define omega minus is the set of parameters in omega such that f of a has an attracting periodic orbit. And omega plus is equal to a in omega, so that f of a has an invariant ergodic mu absolutely continuous with respect to Lebesgue. Right? So these are the 2 physical measures that I talked about at the beginning, right? The 2 fundamental examples of physical measures. I said there's in high dimensions there's a generalization, there's also others. For example, the Feigenbaum parameter A star has a physical measure which is not of this type, okay? And in omega there are many parameters where you also, some parameters where you do not have physical measures, some parameters where you have physical measures of different type, but theorem, a quite fundamental theorem of Lubitsch, the Russian mathematician who works in the States. Around 2000, he proved that omega, the union of these 2, has full measure. In omega. So this formalizes in some sense the idea that these 2 kinds of physical measures are the most important in some sense, so at least are the most prevalent. Right? They're the only 2 that can occur with positive probability in omega. So before I go on, let me just say that how do these arise? So A equals 2 belongs to omega plus, right? We've proved that. Remember, this has an ergodic. So up to A equals 1.4, things are fairly simple. And the picture between 1.4 and 1.2, this is a very bad square. Okay, so you always have this PA, this minus PA, right? And let's say that's something.
Sorry, this omega is 1.422. Is an interval or is just 3 parameters?
No, it's an interval. 1.4, sorry, 1.4 to 2. Because for all the, it's really A star, I really should put A star. Okay, between A star and 2, up to A star we know exactly what happens. Okay, and beyond 2 we also know exactly what happens. Everything escapes except for Cantor's set of points, right? So the interval, what remains is this interval here, where A star is approximately 1.4. I want to write that because to give you an idea of the order of magnitude here. And intuitively, these two, so you can see that this map has some regions where the derivative is big and some regions where the derivative is small. Right? Intuitively, according to the examples we've seen, this kind of phenomenon is associated to having large derivative, bigger than 1. Right? At least these are the examples for which we constructed, the expanding maps. Right? Whereas this one clearly, since it has an attracting periodic orbit, it's associated to having a contraction. Okay? I'm just giving a heuristic idea here. And the reason why this family is so interesting is because it not only contains regions of large, I mean bigger than 1 derivative and less than 1 derivative, but the interaction between the two is very, very subtle, right? And it turns out that both of these phenomena can occur, and intuitively it depends just on whether most points tend to spend most time where the derivative is big, in which case the average in some sense is bigger than 1, or whether they tend to spend more time where the derivative is small. In that sense, in some sense, the average is less than 1, and you get an attracting periodic orbit. And what is especially interesting is that these two sets have very different structure topologically. So this theorem that is from this is from two Polish mathematicians, Gracik and Shantek, and also Ljubich, kind of proved at the same time. Ljubich. This was earlier, actually, 1992. They proved that omega minus is open and dense in omega. With the emphasis being on dense, because open is almost automatic, because when you have an attracting periodic orbit, it always persists for some range of parameter values. What does an open and dense subset look of an interval? This is an interval. What does an open and dense subset look like? Generally. It's a union of intervals, basically. Right? And what can be in the complement of an open and dense set? For example, a Cantor set. Right? The complement of a Cantor set is an open and dense set. Okay? But an even earlier result, let me do a bit more space here. by also Russian mathematician called Jakobson. This goes back to 1981, in fact. What he showed is that the Lebesgue measure of omega plus is positive. It is. It's not exactly a Cantor set, but it's contained in a Cantor set and it has positive measure because it's in the complement of an open and dense subset, so it's nowhere dense.
Omega plus.
Omega plus are the parameters for which you have an invariant ergodic, absolutely continuous measure. Okay? If you remember, it's clear we proved it in this case, A equals 2. We proved it in two ways. For this case, right? We proved it using the conjugacy to the tent map, and we didn't do the full proof, but we showed that you can construct this induced map, right? That's another way to prove that it has this structure, okay? And it turns out that there are many other parameters for which you can do the same thing, and essentially you can construct this induced map, and it has an absolutely continuous invariant ergodic measure. Which means that the dynamics is kind of stochastic. So sometimes, informally, these are called regular parameters, and these are called stochastic parameters. I will say in a second a little bit more about why we have these properties. But let me complete this, and then we just have a couple of minutes break, and then I will finish. Yes, so an interesting question, I think. So I myself, with a Takahashi, Japanese, in 2006, we showed that the Lebesgue measure of omega plus was greater than 10. Okay, that the Lebesgue measure of omega plus was greater than 10 to the minus 5,000. Which, as I used to joke when I was giving the talks on this, you might think it's a small number, but I can give you smaller numbers. So it's not the smallest possible number. The point of that paper was not so much to get that particular number, but to show that we could get a number. And the Jakobson's proof is really remarkable. In fact, when he proved it in 81, he was trying to prove the opposite. He was trying to prove that it has zero measure. He was a student of Sinai, and Sinai gave him this problem. He did for his PhD. Said, prove that we know that this parameter is stochastic. Okay, we know that there's some other parameters, but show that essentially you cannot do it. And he developed a very interesting argument and technique, and this technique has then been generalized and studied a lot. It has become, there's almost a little subfield, which is very much my own, actually, where you generalize to other different kinds of maps with different critical points, and you always try to prove that this set of stochastic parameters is positive measure. But none of those proofs ever gave any quantitative estimate of the measure. That is a kind of natural question. And more recently, Wilczak and Tucker have proved that the Lebesgue measure of omega minus is greater than roughly 0.06, something of the order of 0.06, which is roughly 10% of the size of omega. They actually did it for a different parameterization. There's a family called the Logistic Family. But anyway, essentially the result does this. Strictly speaking, the result doesn't use exactly this family, but a very similar family. But it's clear to everyone that the result should be essentially the same also in this family. So the techniques are very different in these two cases. I'll just mention briefly because it's interesting. In this case, this is a computer-assisted proof, and they literally, with a computer, calculate these intervals because this set is open, right? So it is formed by intervals, and you can literally, with a computer, calculate the exact position of many of these intervals, right? So that's what they do. They calculate the position. They calculate explicitly many thousands of intervals. I don't know how many actually, but thousands of intervals because they're tiny intervals in here, right? But they're only able to account for 10% of the measure. Even though they can do that, there's still 90% of the measure left, and nobody knows if 90% of this measure belongs to omega plus or omega minus. And the technique to prove this is something very different. You cannot, because this is nowhere dense, you cannot put your finger on these parameter intervals. You can, in fact, it's essentially impossible to take. There's only very few parameters that we know belong to this set. Like this one, A equals 2, and there's a few others that have some special properties and you know they belong to this. And so this is a much more sophisticated, well, not more sophisticated, but it's a different kind of argument, more probabilistic and abstract argument that gives that. What I'm working on now is with a couple of colleagues is we're trying to generalize this and do also computer-assisted version, so that the reason we get such a small interval is because we take an interval very close to 2. We take an interval A tilde, where A tilde is almost, so the size of this interval is about 10 to the minus 5,000. So the reason we get such a small number is because we need to take, because 2 is a very special parameter, we need to take a very small neighborhood of 2. So it's not like we look at this whole interval and we get that. So we need to work, because of the techniques, in a very tiny interval. And in that tiny interval, we show that 98% or something like that of the parameters actually belong to this. So the problem is not so much that this method gives a small number, but this method only works in small intervals. So what we need to do is take this, split it up into thousands of tiny intervals, and then try to apply the same method to each of these tiny intervals. Okay? And for that we need to bring in some computer-assisted calculations on these other intervals, which we don't need very close to. So that's how we do it. And then my conjecture, everybody believes that most of the remaining intervals belong to omega plus. So everyone believes that maybe 85%, close to 90% probably are stochastic, but nobody knows. Okay, so I think that's all I wanted to say about that. So if you don't mind, I'll take another 15 minutes because we started a bit late. Yeah, let's just take 1 minute break just to kind of take a breather. This is a little review really that I just wanted to give you a feeling for some of the problems, that we can address. So in the course we were only able to scratch the surface in some sense, okay? So I wanted to focus on this notion of an absolutely continuous invariant algebraic measure, give some conditions for the construction. Okay, this is really just the beginning. And just to give you a feeling, there's many, this second part, which is the verification of the existence of physical measure in specific cases. I just wanted to give you an example in one dimension, even already it's very interesting, even in the quadratic map, which is in some sense the simplest possible map that is not purely expanding or purely contracting, it contains both. And immediately that you get some very, very subtle behavior, like in particular you get this open and dense of one situation and positive measure of the other. Yeah. So there's still open questions for this. This theorem here is very robust, even though it's very it really took a while for people to understand it. It's got some almost probabilistic arguments there. It's very robust and it works for many other maps. For example, in my PhD thesis, basically what my PhD thesis consisted of is a generalization to a family of maps that has a discontinuity with infinite derivative that looks like this. Where you have two critical points, but you have a discontinuity with infinite derivative. There is some motivation for introducing these maps, but and then you move them up and down, and you get a family of maps. And also here you get a combination of large derivative and small derivatives. But the fact that you have a discontinuity creates an additional set of problems. But then you can prove a similar kind of theorem that you have absolutely continuous invariant measure for positive Lebesgue measure set of parameters. Okay, and this can be proved also for maps with many critical points. Okay, so on. On the other hand, this one is a little bit more delicate, and this has been proved also that more generally, if you have smooth maps, not with discontinuity, but if you have smooth maps, in the space of smooth maps, basically in the topology of the world of all smooth maps, then the regular dynamics is an open and dense condition. But this one is really more challenging, it turns out. So this one is not, as far as I know, I think even for the map x to the fourth minus a, this is not known, I think. So x to the fourth looks exactly the same, okay? It's just, this is not a quadratic tangency, it's a quartic tangency, but it looks exactly the same. So many things are very similar, but if I'm not 100% sure, but I think certainly, or if it's known for x to the 4, I don't know exactly. But anyway, this, you cannot, it relies on the fact that you are exactly x2. These other theorems, this theorem, for example, works for this map. It also works for small perturbations of this map. You know, it doesn't use the fact that it's exactly this form. Whereas this result uses exactly this form. You cannot even put a 4 there, or you cannot perturb it. So this is very interesting. So this is the theorem that says that these are the only two physical measures. Right? So in general, for more general situations, we do not know what happens. Okay, let me say before we finish just a few things about the further properties. So one of the directions is to go in this direction where you say, okay, let's find what kind of physical measures you have in a specific system. Another one is to say, okay, once you have the physical measures, what can you say about the system? Right? And so, if you're interested in more algorithmic properties, so this third section is further algorithmic properties. Okay, and I'll just give two examples, first of all, both of which we're familiar with. Suppose you have our x plus alpha mod 1, right, irrational translation, let's call it, or rotation is the same thing, right? And then we have f of x equals 2x mod 1. Okay, so one of them, we can look at both of them either as the graph of a map of the interval, right? So what does this look like? So this is just a translation, which means 0 goes to alpha, right? And then you have derivative 1 everywhere, right? So it's like that. And then we have 2x mod 1, which we know very well is like this. And you can also look at them as maps on the circle, because whenever you take mod 1, so on a circle this is just a translation, right? This is x plus alpha. And here when you look at it on the circle, what is this on the circle? 2x mod 1. It's sometimes called an angle doubling map or double cover, right? Because if you think of this as this is the circle, right? When you take mod 1, it's just a different way of looking at it. And by now, you should be sufficiently fluent with various ways of looking at the dynamics to look at things in different ways. What this is doing is taking 0 and mapping it to 0, and then it's taking this point and mapping it to 2x, right? So if you take a point here, x, it's mapping it to 2x, right? So it's mapping the semicircle 0 to 1/2 is being mapped to the full circle, right? And then this other semicircle is being mapped again to the full circle. Okay? Notice that here, this is a differentiable map. It does not have any discontinuities, right? Here it looks like it has a discontinuity, but if you think of it on the map, then it's just 2x mod 1 is a completely smooth map. Yeah? Because this point is identified with this point, so you just wrap around. As you move around the circle, you wrap around twice. Okay. Now, in both cases, Lebesgue measure is ergodic and invariant. We did not prove the ergodicity in this case, but it's true. Okay, in both cases, for both maps, Lebesgue is ergodic and invariant. So we have Birkhoff's ergodic theorem. Okay? So what does Birkhoff's ergodic theorem says? That we take an interval here, A. Okay? Or we can take it on the circle. I want to kind of just to have it both ways. Right? This is an interval A. This is the interval A. What does it mean? That almost every point spends asymptotically the amount of time it spends in A converges to the Lebesgue measure array. You agree? That's what Birkhoff's ergodic in both cases. But now, the way that these points visit A is very different in the two cases. Right? How does one point visit A? You take a point A in here, right? And what's it doing? It's simply going 1, 2, 3, and it's going round, and it's jumping in A again, then it's coming out, it's going around, it's jumping in A, it's going around, it's jumping in A. It's doing this. How is this point visiting A? It's not jumping twice. It depends on the point, right? So remember, what is the dynamics of these points here? We have all kinds of dynamics. We have dense orbits, we have periodic points, we may have fixed points in here, right? So if you remember the dynamics of 2x mod 1 with this point is doubling. It's not jumping here and jumping back, right? This point is doubling in size, and then it's doubling in size again, and then it's doubling in size again, and then it's doubling, and then some points will come back, some others will be left behind, and then these points will be doubling in size. Some points will come back very quickly, some points will come back after a very long time. Yeah? If we imagine this being very small, it grows, and then when it grows large enough, some part of it must come back, but lots of other parts will not come back. Okay? So there may be, if you remember with the symbolic dynamics, we can easily construct a point that does not come back for the first 1 million iterations. Right? Because there is some point in here, remember we did the symbolic dynamics I0, I1. If A is here, there exist lots of points here whose symbolic dynamics starts with 0, but then has 1 million ones, for example. And these points will spend 1 million iterations in here before coming back, arbitrarily long. So the way that points come back to A is much less uniform and more irregular. Okay? So the Birkhoff ergodic theorem works in both cases, but somehow the way the dynamics work is very different in these two cases. And just the fact that Lebesgue measures invariant and ergodic does not distinguish between the two. In both cases, Lebesgue measures invariant and ergodic. Okay? So is there a difference? Is there a way to formalize the difference? Or is there some significance to this difference? Okay? And this can be formalized in the notion of mixing. Let me add definition here. So a probability, so mu is a probability invariant measure, is mixing if for all measurable sets AB in X, we consider a very general framework here, right? As usual, shall make the definition here. So you take a set A, take a set B. The measure of A intersection F minus N of B converges to the product of the two measures. I will explain a little bit what this means here. So the easiest way to get a feeling for this actually is to write it a little bit different. So this you can write equivalently, you can divide both sides by mu b, and you can actually write this as A intersection F minus N of B over mu b converges to mu of A. Okay, and actually using the invariance of the measure, you can write this as mu of A intersection F minus N of B over mu of F minus N of B, because mu of B is equal to mu of F minus N of B, converges to mu of A. Okay, and then this becomes a little bit more intuitively clear what this is mean, because this is, so you take F minus N of B, okay, whatever this is F minus N of B. And what have we got here? We've got the measure of F minus N of B, right, which happens to be the same as the measure of B, but it has a certain measure. And then here we have the measure of the intersection. And what does it mean to say that the ratio, what this is the ratio. So this is the proportion of F minus N of B that intersects A. Right? That's what this is. This is the proportion. Here you have F minus N of B. Here you have Fn minus B of B. So this is the ratio between the part of F minus N of B that intersects A and this. It's just normalized. It's the proportion of the preimage of B that intersects A. The fact that this converges to mu of A, what does that mean?
Actually, this is another. We can say this is this proportion is measure sequence of measures.
This is a sequence of measures. Yes, this is a sequence. This is converging to the measure of A. The A has a certain measure. Let's say 1/2. Okay, and we're saying that this sequence, so the proportion B may have small measure. Okay, A may have measure 1/2, B may have even measure epsilon. It doesn't matter. And F minus N of B will always have measure epsilon. Okay, but we're looking at how much F minus N of B has very small measure, but it is intersecting A in proportion of Fn minus B. Half of F minus N of B is intersecting A. So essentially what this means is that F minus N of B is distributing itself uniformly in space, because you can think of mu of A as the proportion of A in the whole space. Right? Mu of A is the measure of A. If A has measure 1/2, then half of your space belongs to A, right? And the fact that this converges, that this converges to mu of A is a little bit heuristic, like saying that F minus N of B is slowly filling up the whole space in a very uniform way. So that if F minus N of B fills up the whole space, then the proportion of F minus N of B, not in measure, right, but because the measure of F minus N of B remains epsilon, but it is uniformly spread out. Whatever epsilon measure you have, you spread it out very uniformly, okay, so that the proportion that sits here corresponds to the proportion of the space that A belongs to. And here, right? It spreads itself out uniformly. This is what this means. So, is this mixing? Is Lebesgue measure mixing? Here. Let's take two sets, A and B. And let's take the pre-image of B. So the pre-image of B is just translation. We just take this little interval and we just translate. And then sometimes it will intersect A and sometimes it will not intersect A. If these are small, these two. So can we have this? So when is this? So sometimes this will be 0 here. Many times this will be 0. Okay. Sometimes it may be close to 1. Because it could be, if for example B is very small and A is bigger, there might be some times when the pre-image of B falls inside A. And then here you would have that this is 1, this ratio. Okay? But it might fall, so it intersects. So that ratio will be non-zero, it may even be close to 1. But then there will be several moments when it's 0. In fact, some positive frequency of moments when it's 0, right? Because it will occasionally fall in here, and then it will be all 0. So this is not mixing, this map here. Because you cannot, so irrational rotation. Irrational rotation. So Lebesgue is mixing. I'm not going to prove this, okay? Is mixing for 2x mod 1 for f of x equals 2x mod 1 and not mixing for irrational rotation x plus alpha mod 1. And without a proof, but it's fairly easy to show. You can easily prove that this is not mixing. It is not completely obvious to show that it is mixing, but it's a very good example to try to visualize the property of mixing, because what are the pre-images of the set A? We need B, okay, sorry. So let's take a set B. Yes, let's take a set B. Since we're looking at the pre-images, then let's look at the set B here, right? So this is the set B here, right? So what are the pre-images of B? Two pre-images, exactly. Two smaller pre-images, right? So look, one of them, in this case, intersects a little bit of A, the other one does not. Okay? What are the second pre-images of B? Pick up 4. So you take these two and you look at their pre-images. Okay? And if you see that, so the nth pre-images of B is 2 to the n, small intervals, and they're all very spread out, right? Because these ones are here, then you look at the pre-images here, they will give you 2 images here, and you can see that the pre-images of B are constituted of lots of little small intervals that are very spread out. Okay, then you see, okay, what proportion lands in A of these pre-images? So B might have measure epsilon. Okay, so the union of all its pre-images will have measure epsilon. But if these pre-images are very uniformly distributed here, then this epsilon measure is spread out quite uniformly, and the proportion of those that intersect A, there will be some here, some inside A, some outside A. The proportion will be roughly close to the measure of A, because the measure of A is the proportion of A inside your whole space. Okay? So it's possible to prove that this indeed happened. As you take the pre-images of B, really what mixing is saying is that the pre-images of the set are uniformly distributed in space. That's what really this mixing is trying to say. Okay? And this is a kind of randomness behavior, because what it is saying that if I know that I'm in A and I want to know where I came from, what is my past? Okay? A long time ago, my past could have been anything. Okay? Because I could be anywhere, and if you look at if you know, so there is the, how should I formulate this? So it's a way of saying basically that you lose information about your past, because you could come, you don't know where you came from, okay? Because the pre-images of this interval are spread out uniformly everywhere. So, okay, forget about A, sorry, I formulated differently. So you look at the pre-images of B, they are formulated everywhere. So if I know that I'm in B today, and I say, okay, where was I 1,000 iterations ago, or 1 million iterations ago, the 1 millionth pre-image of B is almost perfectly spread out across your whole space. Okay, so I could have been anywhere. It's sometimes interpreted as a kind of loss of memory, or a kind of random-like dynamical systems, or kind of chaotic. Okay, essentially, mixing is the property that distinguishes whether a system has a kind of what we loosely talk about as chaotic dynamics, as opposed to this kind of situation, which is much more regular. Okay, in both cases you have Lebesgue, his ergodic and invariant maps, but here, since I know that I come back more or less every 20 iterations, and I want to know exactly where I was 1,000 iterations ago, okay, I can more or less calculate more or less exactly where I was 1,000 iterations. Whereas in that case, I'm much more spread out. Okay, so I think I will not go further. I mean, just heuristically, let me say that one of the interests in, you can go further. This is just an example of how you distinguish two different systems. At one level, you start with Lebesgue ergodic and invariant, so you have Birkhoff's ergodic theorem. It's the first level of statistical description. Mixing is an example of the next level, right, where you distinguish between these two. Then you can say, how fast is this mixing? Okay, so you can ask, does this have some kind of speed that depends on the system? It turns out that you need to change the setup a little bit, but you can talk about how fast things mix. It's called decay of correlations, because you're kind of losing correlation. That's what this mixing is about. And there are many results about different systems having different decay of correlations. So 2x mod 1 has one decay of correlation, but if you take the x squared minus 2, you can also study the decay of correlation there. And then there's many other statistical properties. So this is really where the probability theory can be brought into a lot of results about the probabilistic statements about independently distributed random variables, for example, can be translated, and you can try to get similar results here. Okay, so these are the two main strands. The existence of physical measures in different systems, but then also looking at once you have a physical measure, looking at the statistical properties, and mixing as a good example of that. Okay, so this is a little bit of a view for those of you who want to do more, or for an idea of how it continues. So thank you very much. for participating in the course. I hope it was interesting. Good luck. Okay.